Well, believe it or not, this is the last lesson.
I know.
Well, I'm glad you know. So, we'll start talking about Stokes' theorem. And what on earth is Stokes' theorem? A Stokes' theorem gives a relationship between a surface integral over an oriented surface S and a closed space curve C, a line integral over closed space curve C, forming the boundary of that oriented surface S. An example would be to connect the circle centered at the origin of radius 2 in the xy plane that forms a boundary of the hemisphere z equals square root of 4 minus x squared minus y squared. By the way, you recognize if you squared both sides, you get eventually x squared plus y squared plus z squared equals 4. So it's a sphere of radius 2. This is only a hemisphere because z equals the positive square root only. So in order to get a graph of this, I got to slip in the spherical coordinates. By the way, notice here's r cosine theta for the x, r sine theta for the y, and 2 times cosine. Remember the radius of the sphere is 2, so 2 times cosine of phi for the z. And here is our hemisphere, that's in yellow, and the border of the hemisphere in the xy plane is the closed curve C that we're talking about. So I guess we should look into Stokes' theorem.
It's almost time.
Yes, it is time to look into Stokes' theorem. And here's what Stokes' theorem says. Let S be a simple oriented surface, like our sphere above, with unit normal vector n bounded by a piecewise smooth simple closed curve C, like the circle in our above example. So if F is a vector field whose component functions have continuous partial derivatives in an open region containing the curve S, then look at this, the line integral over curve C of f dot dr is the surface integral of curl of f dot n, that's the normal vector to our surface S, ds. So, recall from an earlier unit, actually unit 5, lesson 1, the memory device for calculating curl of f is defined on a vector field f equals mi plus nj plus pk is as follows. We have I, j, and k across the top row, partial with respect to x, partial with respect to y, partial with respect to z across the middle row, and m, n, and p, all functions of x, y, and z across the third row. So, we'd like to verify this theorem, and let's do so. So we're going to verify it for the hemisphere, x squared plus y squared plus z squared equals 9. And z is greater than or equal to 0, so you realize that is just the hemisphere. That z greater than or equal to 0 says the upper half, right? And with the vector field f equals yi minus xj. So do this as a line integral without Stokes' theorem. We need a vector valued function for the border, which is this circle, x squared plus y squared equals 9. Well, duh, the vector valued function for that, you could have gotten this from parametric equations from pre-calculus, I think. So 3 cosine theta times I plus 3 sine theta times j, theta going between 0 and 2 pi. So then dr, if this is our r, dr, the derivative of cosine is negative sine, so negative 3 sine theta I, and derivative of sine, of course, is cosine, so plus 3 cosine theta j d theta. And so our f dot dr, well, f is this vector field right here, but when we replace that vector field with what it is, yi minus xj, there's the yi minus this xj, and then dotted with this dr vector, we wind up with, let's see, this, here we go, this times this is negative 9 sine squared theta, and this one times this one is negative cosine squared theta, so we wind up, sorry, I should have said negative 9 cosine squared theta, so we wind up with our negative 9 factoring out, negative 9 times sine squared theta plus cosine squared theta, so it's just negative 9 d theta, and the integral is 0 to 2 pi, remember it is a circle after all, negative 9 d theta, which is negative 18 pi. Now we can do it as a surface integral using the curl of f, right? Remember, this is how we're going to do this time. So curl of f, let's see, ijk across the top, our m is here, our n is here, and so we say it'll be I times this partial, which is 0, minus this partial, and the partial with respect to z of x is 0, so we just got 0i, and then minus j times this partial, which is 0, minus a negative, so you could say plus, or it doesn't matter any way you do it, it's going to be 0 anyway, because partial of y with respect to z is 0, so we got 0i plus 0j. Now we do get something from k. K times this partial with respect to x is negative 1, and this partial with respect to y is minus another 1, so we got negative 2k. So a normal outward vector to this surface, remember, sphere, radius 3, remember? So normal vector would be partial of this with respect to x, which is just 2x, over, remember it's got to be a unit vector. Well, partial with respect to y, okay, 2y, partial with respect to z, 2z, and then it's got to be made into a unit vector, and so that would only happen if we divided everything by 2 and then divided by the length of the vector. And so we would wind up with, this is our normal vector, here's the whole thing, or normal vector, but what you're thinking, well golly, that's complicated, but it's not so complicated, because square root of x squared plus y squared plus z squared equals 3, remember? It's a sphere of radius 9, so the square root of 9 is 3, so duh, okay? So we wind up with this nice vector here as our unit normal vector, and then we've already got the curl, that was just negative 2k, and then we're going to dot that with this unit vector here. Well, negative 2 was it negative 2k? Yeah, negative 2k dotted with this is negative 2z over k, because the I component and the j component are just going to be 0, so we got negative 2/3 z. And so the region R is this circle in the xy plane, so wisely we would switch to polar coordinates. Yeah, we're not stupid. Well, you're not. And we're going to make this substitution 3 over z dA for ds, since ds, remember how we find the ds, 1 plus partial of x, f with respect to x squared plus partial of f with respect to y squared. You should remember that from integrating surface, so surface integral. So that dA, which, okay, now this partial is here, this partial is here, and if you do all the math on this, this is 9 minus x squared minus y squared over 9 minus x squared, or sorry, and then plus x squared plus y squared over 9 minus x squared minus y squared. The whole thing turns out just to be 9 over 9 minus x squared minus y squared, but remember 9 minus x squared minus y squared is another name for z squared. So that's just 3 over z dA, like I said up here. That's where that came from. So we wind up getting this integral. Now keep in mind, R is our circle here. So R goes from 0 to 3. This was our curl dot n. This is our d. This is our, well, 3 over z dA is our ds. So, and this is the r d theta is the dA. So we got 3 over z times that. And what happens is the z's cancel, the 3's cancel. r goes from 0 to 3, theta goes from 0 to 2 pi, so golly, this comes out nice. It just comes out, we wind up integrating negative 2r, and so that would be negative r squared going between 0 and 3, so that's negative negative 9, and then integrating negative 9 with the variable theta going from 0 to 2 pi, we get negative 18 pi. So either way we do this, we get negative 18 pi. How about that?